Okay, I'm going to do a quick summary of what I've said about these graphs of basic functions. This is a quick summary of probably 30 minutes or more of deeper explanations or more slowly paced, and where you see me actually doing the constructions. And you want to at least watch me do the construction of this one and get the idea. Okay, but anyhow, this is a graph of y equals 1 over x. You see I've plotted the basic points in purple. Then I've drawn the curve for the extended basic function. And one thing we note is the graph of the extended basic function doesn't do like the white graph here. It doesn't level off. At least doesn't level off anywhere above the x-axis. It approaches the x-axis. It keeps getting closer and closer to the x-axis. Sometimes I'll see a graph that looks like this. And a graph that looks like this isn't the best thing because in the first place, this isn't a graph of the basic function. This is a graph of part of the complete reciprocal function. The basic function only extends from -2 to 2, and the extended basic function only extends from -2 to 2. Now the point 0, 0 is omitted. We have asymptotes with the y-axis. As I explained in more detail, the closer we get to the y-axis, the smaller this number gets, and the more times it goes into 1. No limit to how small the number can get, no limit to how many times it can go into 1. So this graph becomes asymptotic to the y-axis. We don't plot points when we're doing the basic function any closer than this, but this is the behavior. And it's actually symmetric with what would happen if we extended the graph in the positive x direction. Let's not worry about that. Let's just worry about a couple of things. Make sure that we graph this thing, that we scale these axes. The first thing I do, and again you want to watch me do this, is I locate the points 2 and -2 and make sure they're pretty well symmetric with the origin, and the 2 and -2 here, the extreme points. Then I subdivide this interval in half, giving me 1, divide this interval in half to give me half. And same thing over here, same thing here, same thing here. Okay, now to graph 1 over x squared, we note that y equals 1/4 is in the range of the basic 1 over x squared function, so we're going to need to scale our graph so that we see where 1/4 is, as well as 1 and 4, because those are the values in our range. So here we have the points, okay? You see the interval from 0 to 4. Half of that interval is 2. Halfway, the midpoint of the interval from 0 to 2 is 1. And then we subdivide that in half to get 1/2. Subdivide that in half to get 1/4. Let's close this laptop so we don't run down the battery. I keep forgetting to do that. Okay. And now we can plot the points, and then we can sketch the curve. Now the first thing we do is we plot the basic points, and we make sure the basic points that we plotted are visible on this curve. If we don't have the basic points, we're not going to get the curve right. Now we're not going to get it 100% right anyhow because it's a hand sketch, but we want to have, as carefully as possible, we want to have the basic points located accurately so we can sketch a good curve. And again, in the other videos, I do this in detail, so if you need to see that, very good, you'll have it. I do the same thing for the exponential function. Exponential function is pretty easy to graph. The basic function's only defined for the integer values because we can't do the exact values at any other numbers. Okay, we can't figure out the exact value of an x that gives us an integer or a rational value of 2 to the x, and we can't figure out, given a value of 2 to the x, even a rational value, we don't have a rational value for x except at the integers. Okay, so anyhow, here are the 5 points that we get. That the process for setting up the graph is identical. I did a little extra with this, and I'll come back and talk about it. And actually, I'm not going to talk that much about it. It's worth watching that particular video. The x cubed graph. We have the problem that the range of the x cubed graph consists of 0, 1/8, 1, and 8. Now, 8 is a whole lot bigger than 1/8. It's hard to show them both on the same graph. For example, here's -8. Subdivide this interval, we get -4. Subdivide that, we get -2. -1 is just this big. And now we've got to do 1/8 of this. So we've got to subdivide this in half, subdivide that interval in half, subdivide that interval in half. So 1/8 is going to be very, very close to the line that we have for the x-axis, just a tiny bit below. So it's a challenge to do this accurately. It'd be easier if we had a bigger, a longer y-axis compared to the x-axis. You can certainly do that when you do your own sketch. Okay, well, anyhow, here in purple are the points. Note that the -1/2, -1/8 point and the 1/2, 1/8 point are very, very close to the x-axis. Sketch the extended basic function, graph the extended basic function, and there we have it. We can do estimates. Okay, now over here, just briefly what I did was I did an estimate of 2 to the 1/2. Okay, so here's 1/2, we come up to the graph, we project over to the y-axis, and here's our graph, here's our representation of the value of 2 to the 1/2 power. Okay, well, that representation isn't completely accurate. My projection lines aren't that straight. That probably should have gone up to the middle of the orange line, and I kind of stopped at the bottom. So there are little flaws in this. But the point is, we can see that because this graph is increasing more and more quickly, it's concave upward, that the graph of the 2 to the x function lies below a straight line graph between these two known points. Now the halfway point on the straight line graph, I've got a very tiny, very faint straight line drawn here, but hopefully you can see it. The y-coordinate is halfway between 1 and 2, because it's a straight line. And this point is halfway between here and here. So, for reasons that should be pretty apparent, this point should be 1.5, halfway between 1 and 2. Doing a decimal estimate, well, down here we see a little more clearly. If these are the 2 points, here's your x equals 1/2 point on the curve. It lies below the straight line. The halfway point on the straight line should be at 1.5 on the y-axis, so 2 to the 1/2 should be here. You draw that carefully, and it'll look much like this. Doing an estimate of this point, we figure it might be 1.3 or 1.4. If you have a really good graph, you'll be able to tell whether it's 1.3 or 1.4. But a lot of hand sketch graphs are going to have the possibility of easily being off by 1/10. I also estimate the value of y for x equals 1.3. First locate 1.3 by subdividing the interval from 1 to 2 in half, and then 0.3 will be closer to the 1.5 than to the x equals 1.5 point than to the x equals 1 point. I could attempt to divide this equally into 5 subintervals. 1.3 is going to be around here. Okay, I project up, I project over. So here is my estimate of 2 to the 1/3. I've got question marks around that estimate. The question is, do we have a good estimate or not? Okay, now I say 2 to the 1.3 equals, and I should use wavy equal signs to indicate that it's an approximate equality. Because of course it's an irrational number. Decimal equivalent goes on forever. Looking at where this is between 2 and 3, we estimate this might be 2.3 or 2.4. Well, that's a quick synopsis of, that's a 10-minute synopsis of probably 20 or 30 minutes of video.